Hello, and welcome to the third of my 3 sessions here at this conference. I don't know who was here for the session yesterday. Yesterday was fairly intense. Today is going to get worse. My name is Clemens. I'm the lead architect for the messaging services in Azure, Event Hubs, Service Bus, Event Grid, Relay. And also in our team is also Azure Stream Analytics, very important specifically for this topic. And I will tell you about Azure Event Hubs, not as an introductory course. You will not learn how to send and receive messages. I'm assuming that you know this. And I will give you a tour through features, things you may not have seen in that way yet. And I will go into details on networking, architecture, especially on how Event Hubs Premium works. And then I will also talk about reliability and also performance at the end of it. So I'm going to do a fairly brief overview of what Event Hubs is and some features. And then we're going to go into clusters, namespaces, networking, authorization, partitions, log storage, and all that stuff. What is Event Hubs? It's a platform as a service event stream broker. You can use the Apache Kafka API with it as one of the options that we have. You can send with HTTP, with AMQP, and with the Kafka RPC protocol, and then use all the Kafka RPC clients. I'll talk about that. But with lower cost and better performance and less effort. It's fully managed, which means we deal with CPU and disk and all those things for you, and I will explain to you how that we do this. It's compliant with AMQP 1, which means you can take any arbitrary AMQP client and send and receive from Event Hubs. And it's also wire compatible with the Apache Kafka broker. And it has a polyglot set of SDKs that support multiple languages. And as I said, we have industry-leading reliability and availability. To that I come at the end, and it's fast. Yes, that's a very busy slide. And I will share those slides, and I'm not going to spend much time on this slide. The point is, it is similar to Kafka from the outside, but it's not Kafka. And I will read some of that for you because you can't read it. User model so the user model is the same. It's a partitioned event stream broker with high availability replication. The architecture, however, already differs. Event Hubs is a multi-tier, multi-tenant broker system, while Kafka is a single-tenant monolith that you have to go and use external software with for managing it and for setting it up and for bundling it into a cluster. Like all of that stuff is already done for us. Implementation language is C# and native code, C and C++ in Event Hubs, and it's a Java platform in Apache Kafka. And we'll learn about all the things that are kind of on the Event Hub side, but they're fundamentally different. So we don't use any of the Apache Kafka code base, but we implement that exact same protocol. Just for your understanding, we have an entirely different architecture for Event Hubs. Before I get to technical details, let's talk about SKUs and pricing because they matter. Because I will also I will explain the differences between those two things, or these three, and to point out that this is not an arbitrary feature switch that we make. It's not that with Event Hubs Premium, when you buy this, we're turning on 3 switches, and then you get more features. But it's really a fundamentally different architecture under the covers. They just look the same from the outside. They have the same API surface area. They have the same protocol gestures that they support, but ultimately the capabilities are based on different architectures. Event Hubs Standard is our shared resources model, which means you are buying effectively capacity in a cluster with other neighbors on the side, which means that we can give you very, very, very cheap pricing. We can make it, you can run an Event Hub with one throughput unit for a month for $20, which is, of course, completely unthinkable when you run a VM with Kafka on it, or even when you have to go and run a Kafka server that's running managed. It's ultra cheap. And you can go and scale that up to 40 megabytes per second in ingress and 80 megabytes per second in egress by buying further throughput units. And throughput units get you effectively a quota allowance on our cluster. Event Hubs Premium is an isolated resources model. I'll explain that. And that's a capacity-based pricing model, and then goes up to 120 megabytes per second in ingress. And you buy these premium units. And the concept there, if you are familiar with or heard already the session yesterday about Service Bus, that is then a very similar model where we give you effectively a slice of a cluster in terms of compute and memory that you can then use. And that also then enables features in a bit of a different way. And then with Event Hubs Dedicated, that's for the most demanding workloads, where you are effectively getting an entire cluster of Event Hubs for yourself. And these Event Hub dedicated clusters can be growing more or less boundlessly, only limited by your budget and by your needs. And the biggest Event Hub that we currently run for an external customer runs 3.5 gigabytes per second sustained workload. So those can do quite a bit of work. So these are the different tiers. An advertisement, briefly. If you run Apache Kafka in your own data center, you can replace it with Event Hubs. We run that cheaper for you, and we might be just close enough from a latency perspective, because we're super fast, to be even better than the Kafka broker you run. So that's always a possibility. Just as with Service Bus, you don't have to run the workloads in the cloud. You can run the workloads on premises where they are, but you can simply swap out your cluster by using the one that we give you. And as I said, the economics are unbeatable compared to running a Kafka cluster by itself, which is quite the Tamagotchi. Okay, so after all the business model and advertising and all this, let's go and dive more into the details. What is an Event Hub namespace? Event Hub namespace is effectively the virtual broker that you're getting. And you will, if you were here yesterday, you will notice this picture is exactly the same as for Service Bus. Not exactly the same, but very similar. What we create when you create a namespace in Event Hub Standard and Premium is we give you an allocation in an existing cluster, and then we will go and create a name for you, a DNS name, and then effectively alias that to the cluster address. So every Event Hubs broker is a virtual broker, if you will, and that virtual broker always has a public IP address by default. You can turn that public IP address off, and you can also bind that Event Hub namespace to a VNet, and then make that part of your VNet. So that's all magic that's happening in networking that I'll explain later in more detail. Inside of that namespace, you can then go and create these event hubs, and an event hub is equivalent to a Kafka topic. It's actually, from a Kafka perspective, if you look at it at event hubs from the Kafka API perspective, it's exactly the same. That topic, or event hub, is then split into multiple partitions. And really what the event hub is just a bracket, a name effectively for these partitions. And the things you're interacting with as a sender are these partitions and what you're also reading from. What you can read through are consumer groups, and these consumer groups exist to coordinate the consumers to make sure that you have, if you have 8 readers, that those 8 readers are pulling from, not pulling from the same partitions, but 8 readers pull from 8 separate partitions. That coordination is done through a consumer group. So it's a virtual broker. It's not a VM. It's a part of a bigger cluster. An event hub, per se, as shown in this picture here, is, as said, a name that has partitions Each partition is a log that is durably triple replicated in an append-only data structure. Each partition is mapped to a storage account, as we'll see. And that partition has a throughput ceiling of about between 5 to 10 megabytes per second. That's as much as you can do, which means if you need to have more throughput, you need to have more partitions. And that's why all of those event stream brokers with these enormous throughputs have more and more and more partitions. And the way how partitioning works is that you basically tell the event hub, either from the client side, to go and set a partition number, so you can address those directly. You can set a partition key, and then we hash that and map that to a partition consistently. Or you just leave all the partitioning hints off, and this is different from Kafka, and Event Hub will make the decision for you of where to place that event. So you can use effectively Event Hub as if the events are not related, you can basically just dump events into Event Hubs, and it will go and balance the load across those partitions. The consumer group, the way how you get data out of it, is a coordination mechanism. With Kafka RPC, the broker assigns the ownership to the receiver. So you have a set of receivers that are receiving through a consumer group, and the management of which consumer owns which partition is something that the broker helps coordinate. The broker assigns that. Using the AMQP approach, you can have an external leader election of any sort. And then you can effectively have there's a circuit breaker mechanism, an epoch as we call it, that allows effectively an external client to go and take over a partition. So we're allowing for external and a completely externalized leader election model for determining who owns what. So that is enabling things like Service Fabric, Orleans, any of these cluster fabrics to kind of determine who owns what, and then for the clients to go and realize that on the broker. We will also, later this year, implement the server-assigned model over the AMQP protocol so that you have both choices on the AMQP front. The difference between Event Hubs and Kafka and a queue broker is that the clients, the consumers, are scrolling over the log. So the consumer chooses an initial offset where they start reading in the log, either at the newest or the oldest or somewhere in the middle. They can provide a timestamp. And then they keep reading onwards. And then they can go and reset and reread that stream. So the way how consumers consume from these event streams is completely controlled by the consumers. There is no bookkeeping, as it is with a queue broker, as it is with Service Bus, about the delivery state of every individual message, which means Event Hubs is not a queue. Neither is Kafka. So if you're finding yourself implementing a queue pattern using Event Hub or using Kafka, you're choosing the wrong technology. You should be using Service Bus. But it's optimized for reading and rereading streams again and for syncing across time. Right? That's what that's built for. And it's very fast. And to be very fast, it needs to have very few features. And so all the filtering and all that bookkeeping, it doesn't exist in Event Hubs by design. Event Hubs Capture is a feature you can turn on Event Hubs, but it's good to look at Event Hubs Capture really as a separate lens that you can look at Event Hubs through, because Event Hubs is a batch capture mechanism. So just as with the Event Hub that you consume from, and you can still consume from these Event Hubs when they have capture turned on in a normal way, you are producing into the Event Hub using any of the available APIs. And then the capture engine runs when you turn this on. This costs extra in standard. It is included in premium and dedicated in the pricing. And that will then go and read those partitions and by a policy which is based on a time limit or a size limit, you can say, please write a blob every 1 megabyte, or every 10 megabyte, or please write a blob every X minutes. Based on that policy, we will go and write those events into blob storage or into Azure Data Lake Gen 2. And then you can go and make these you can apply the lifecycle policy of blob storage, and you can effectively make them, turn them cool, and then turn them into the archived state automatically by policy, which means you can keep your events forever in these batches. So it's an automatic export. The latency is really your time limit here. So if you set the time limit here to 10 seconds, your delay from ingress to the batch data being available is 10 seconds. So that allows you to do batch processing, for instance, with Spark or other engines that are batch-oriented in a very fast way. I'll get to those archives in a second in more detail. So whenever one of those capture files has been written, we're raising an event also into event grid so that you can then go and from the other side go and pick this up. So think of this as a feature that is really its own concept, where we allow you to go and push data in, and we organize batches for you. And those batches here end up being in a folder hierarchy in blob storage, which is your event, your namespace, and then your event hub, and then the partition number is labeled in here. And then furthermore, we organize those folders by time, date, etc., and that path is actually configurable for you. Okay. What we're writing with Event Hubs capture are Avro files. And the reason why we chose this format is that it's nice and compact and carries the schema with it. So it's Avro container files. A common misconception is that this makes a statement about the data that's inside of those events. Has nothing to do with it. So we're simply storing the raw event data as Avro, and that's a choice that we make because of the compactness of the format. That doesn't mean that if you are preferring Parquet, or if you're preferring XML, or if you prefer JSON for your payloads, that you can't use that with it. It's completely independent. The payloads stay as byte arrays. So we write these archives. These archives, each of them has this format, where we have an Avro file header with the embedded schema, and then every event is being packaged with a header. That's the way how our format works, and then the event properties, and then the raw event data as bytes. Okay, the way how you process this is you can go and react to the grid event that we raise, and hook up a processing function, Azure function, for instance, that is subscribing to this event. Whenever we write a file, we will raise that event, that function is getting triggered, that file will not, the path to that file will be conveyed in that event, and then you can go and pick up the event. You can use an Avro library, go and crack it, and we have samples for how you do this, and then you effectively get the raw events in your hands, and then you can use your own decoder, right, a JSON encoder or a Parquet encoder or whatever, and get the data out, and then move that onto whatever target you want to. And so there's plenty of examples that we have on the website which show you how to do this with Spark and how to do this with how to do transcodings, and so how to do this with various analytic systems. But one, Event Hubs with consumer groups and consumers is kind of the stream-oriented model, and Capture is a batch-oriented model that's optimized for batch-oriented workloads. It's not a publish subscribe broker. Partitions are not subscriptions because they're chosen by the producer on the broker, right? So it's not a pub subsystem. Specifically, it's popular in the Kafka world to say, we do pub sub with Kafka. Well, you can't, because the subscriber has no say about the layout of the data that's arriving. It can only pick a partition, and that's the best it could do. But that's not a subscriber. In PubSub, a subscriber has the choice of effectively creating their own subscriber stream, and then they typically also allow for filtering. So that's not PubSub. It's a partition exists to allow for parallelization of processing. It's not there to kind of discriminate between different kinds of data and do PubSub. Yes, you can do that in edge cases. There's no absolute truth. But commonly, if you only have one pony, right, and that pony does just one trick, well, then everything looks like that pony, that trick. But if you have a PubSub broker, like Service Bus or like Event Grid, go and use that. It's not a queue broker, I already mentioned that. It's also not a discrete event distribution engine, right? It does not push deliveries. It doesn't track delivery failures as you are calling webhooks, etc. Event Grid does that work. And it's also not, and that's also important, not a long-term event store. It's a terrible database. And I'm saying that about my product. So if you are of the school of event sourcing, or if you believe that all the events of the world need to be stored forever, and then you really think that you need to go and dig into, you want to reconstitute a database from original data that is 4 years old, okay. But that is not the architecture for that. As data ages, you need more indexing. Because you will be interested still in events, but in slices of events. And the only thing that Event Hub does, and Kafka does, is it organizes data for fast retrieval along the time axis. That's the only index it has. So it's not a database. The way how you deal with databases, how you deal with streams, is you load from Event Hubs into a real database, your choice of Azure Data Explorer, or into SQL, or into Cosmos, and we have many, many databases for that purpose, into the appropriate one, and then you retrieve that data better indexed from there. But if you need to have data within 10 milliseconds from ingest, then Event Hub is the choice. So it's your ingest point, but it's not your database from which you will read in the future. And the great thing about eventing is events never change. They're facts, which means you can create as many copies of them as you like. Okay. Event Hubs is compatible with all the producer and consumer APIs of all current Apache Kafka clients. Right? There's the only real Apache Kafka client is the one that's in the Apache project, and that's built for the Java and JVM. That is the only thing that is actually an Apache project. And then there are numerous other libraries in various states of supportability. And the library that's kind of the other big library, effectively, is the C++ librd Kafka library that's built by this gentleman, Eden Hill, from Confluent. And then there are popular libraries here, Python, Go, .NET, that are then binding to that library, also from Confluent. And then there are effectively several other libraries here, but ultimately the open source, really free and community-supported version is only the Java version of Kafka. But we're compatible with all of them. But we don't have our own Kafka client, right? If you want to have Apache Kafka, use the Apache Kafka client. The Event Hub SDK speaks AMQP, so it speaks that open protocol that we negotiated in Oasis with a number of partners. We have an extra technique, effectively, for how you set the offset, how you declare the offsets, and we document this in our documentation. See how you set this, so you can go and do this also with your own AMQP stack, if you will. But this is all built into these open source libraries that we have for Event Hubs. So you can also go and look at this if you want to go and copy it. And we have this for .NET, Java. We have Java Spring Boot support for the Cloud Stream Binder, Python, TypeScript, Go, all those languages, and all those libraries are open source. So you can go and look at them and also build variations of them if you want to. As said, we're compatible with generic AMQP clients. The great thing here is that the send side of Event Hubs and Service Bus are completely compatible. They look exactly the same. So you can actually go and take the Service Bus client and send to Event Hubs, and you can take the Event Hub client and send to Service Bus. The receive sides are different because one is a queue broker and does queue things, and the other one is an event broker and has this offset handling, right? But they are, from the send side, they're completely compatible, which means you can go and target a generic AMQP client, but also our clients, at an event hub or at a service bus, and there will be no difference. And that's the strength here of that model of using AMQP, is that you have that flexibility. And of course, with the generic AMQP client, you can also point it at ActiveMQ or at RabbitMQ or any of those brokers that support AMQP. Okay. Let's go and look at the details of the internals. The logical architecture of Event Hubs is that it is a 3-layer system. That is more true for Event Hubs Premium, as you will learn, than it is for Event Hubs Standard and Dedicated at the moment. But that will morph into a 3, so it's 2.5 layers effectively for those two latter brokers. But we're adopting this new storage model across the board for everything. So this is just a point in time observation. And what I mean with 2.5 layers or 3 layers is that in Event Hubs Premium, which is the latest technology generation, we have an extra storage engine that I will explain in a moment. The role of these layers is that the gateway deals with everything that has to do with networking and authorization, and including the protocol handling. So it speaks AMQP, it speaks Kafka, and also does normalization, which means everything that comes in Kafka over the Kafka protocol actually gets normalized back into AMQP, and everything goes out via Kafka gets effectively denormalized from AMQP. So we have one canonical internal format, and that's the AMQP message format because it's the broadest set. You can send using Kafka, you can receive using AMQP, you can send using HTTP, you can receive using Kafka, every combination works. Transport security, I'll talk about with a separate slide. And then the backend does a bunch of work for related to the messaging, meaning taking the messages and putting that on disk and organizing it, and the storage backend then deals with actually putting it on disk. So there's a relationship here between the backend and the broker. We'll talk about that. The premium units that you're buying with Event Hubs Premium buy isolated capacity at this layer, at the backend layer. Right? The rest is always shared. The gateway is always shared. Okay. What's super important for us is reliability and availability, and to make sure that you can keep working when things fail on our end. When we have hardware failures in any component, a machine fails, something inside of a machine fails, the power supply for a rack fails, the networking for a rack fails, the networking for a row fails, any of those things. If a jumbo jet barrels into a data center facility and destroys it completely, your application should continue working within SLA. That's a goal. That's what we do here. So fault domain placement, a fault domain is effectively a rack or a row of racks, right? If that fails. So what we're doing is we're placing our cluster across several fault domains, and we're making always sure that resources that belong to you and your workload never exist in the same fault domain. That's the placement policy. Furthermore, in all availability zone enabled data centers, which are all the big ones, we also spread a cluster across those 3 availability zones with 3/3. And the capacity is such, if we lose 2 of those facilities, we will still maintain SLA. So if there is a natural disaster in that data center region, like a tornado goes through it and hits not only 1 but 2 of those data centers, the remaining one will stay online because there's independent power, there's independent network, there's independent everything. It's a separate data center, and they're interconnected such that they form effectively one logical unit, but they're completely separate facilities. So we are placing our clusters across those boundaries, and they act as one. You don't see any difference, but they're physically separated. here's how this looks. In a availability zone, we make a deployment of VMSS, or across availability zones, we make a deployment with Azure Virtual Machine scale sets. That is already aware of these constraints. So that knows about availability zones, that knows about fault domains, and it places our VMs. For Event Hubs Premium, we have now switched to a model where we take isolated VMs, which means we take the entire hardware machine with one VM. With the other versions, with Event Hub Standard, we actually have relatively normal 4-core VMs that we then spread across. But for Premium, we now have full VMs with up to 88 cores that we run on. And we run then very many of those. So these are very large clusters. And the reason why we need that many cores, I will explain in a moment. And then on top of that, so this makes a cluster. We then basically put a ring structure around those VMs, and that ring structure is created by Service Fabric. So Service Fabric is our cluster manager that we use, and that is doing two things. First of all, it selects which VM is executing which role. We have these backend roles, we have the broker roles, and we have the storage roles. And the assignment of which role runs where is something that Service Fabric does for us. It does the placement of that workload. It also then helps us finding leaders. We, for instance, need to have a leader for who owns which partition, where does a partition live, and then where does the secondary, where the secondaries, effectively fall over points in the different availability zones or in the different fault domain lie if the primary dies. All of that is done automatically by Service Fabric. So everything is automated here. There's no manual intervention. Nobody thinks about the VMs or the processes or the workloads. When a VM goes away, it's automatically replenished. If the cluster grows or shrinks, which it only does under controlled circumstances, we don't do auto-scaling ourselves. We can inflate clusters. We rarely shrink them. And we also rarely inflate them because we have a pretty well-oiled machine for knowing how capacity works these days. But everything is done by Service Fabric. The upgrades that we do are also orchestrated by Service Fabric, meaning that if we add new software, Service Fabric will take down parts of the service completely transparently. We'll go and add the new software. We'll go and reboot those machines and then take the next set of machines down. That's all happening under full load. And you don't see it. And we're staying not only within SLA, we're staying enormously above SLA as we do all that work. So we have very smooth ways of kind of disconnecting, moving clients as we're preparing for those things. So upgrades is something that you don't see. There are no service windows. We don't need to announce when we do an upgrade, because we have done this for coming up on 10 years now with Event Hubs, and this is a very established process. The allocation of namespaces to clusters is based on heuristics. So we have a notion of what the average Event Hub standard namespace needs in terms of capacity, and so then we allocate based on capacity to those namespaces to those clusters. Or they're based on the reservations that you make, and also some heuristics on who will auto-scale and who not. So these are all, we're pretty, we're optimizing effectively how the capacity that we have in the cluster then basically maps to customer namespaces. So then you have too much overcapacity, but always enough capacity to go and deal with failures, and also to deal with your scale-up demands. The gateway and the backend have different ways of placing workloads. So these are effectively, that's the result of the assignment of Service Fabric picking VMs effectively. So we have VM 1 and 3 and 5 and 7 and 9 and 11, 13, 15, 17 are playing gateway roles. And the other ones here are playing backend roles. That's, again, that's arbitrary numbering. That's something that Service Fabric does for us. So we only say in the policy, hey, we want to have that many front ends and that many back ends, but that's effectively the choice that's being made. The Apache Kafka clients, when they talk to us, if you are familiar with Kafka, Kafka has a notion of a bootstrap address, and that's one of the brokers. And then you talk to that broker, and then the client will then, depending on which partition you want to go and talk to, connect directly to those individual brokers that own those partitions. We don't have that here. So effectively, we have one address, and we will tell the Kafka client, for every partition, come to this address. And then we're going to do the dispatching here. So that allows us to do all the networking policy only on one IP address, and all the networking management. That also allows customers to do firewalling, right, just with that one address, and not having to deal with multiple addresses and expanding the surface area. Because this was built for public IP space, right? And it wasn't built for like the internal needs of a company, which Kafka originally came from, right, for LinkedIn. The workload placement in the gateway is happening by the client. So the load balancer places a socket and then effectively chooses one of those process containers. So that's normal as it would be in a website. And then all state that accumulates is the minimal state that accumulates on the on a connection. For instance, as you're iterating over messages in an AMQP, on an AMQP link, all that is also managed in the gateway. The gateway is also responsible for communicating with AAD. There's a model here that we employ in Azure where when you are requesting a token from AAD, you're requesting a token for a particular service and the rights and the roles that are associated with that service from AAD, but that's not an authorization token per se. It doesn't confer the exact permissions yet on that particular entity because it's a longer lived thing. So between the time that the token was issued and the time that you're doing an operation, there's some time where you can actually go and still do changes in the policy, and there's a circuit breaker mechanism here. So we take the token and then pass it to Active Directory with the request of whether the particular resource, the event hub, or this consumer group can be talked to, and then we get back an yay or nay, and then we're going to go and act on that. The backend is different. The backend is the placement for those workloads happens through Service Fabric, where the partition is then owned by a process. So there are X partitions that exist in the cluster, all belonging to different event hubs. And as they get activated, meaning someone asks to get messages from them or someone asks to put messages there, then the partition gets activated and gets assigned to one of those processes. And then Service Fabric is maintaining effectively a lookup table that is then used by the gateway to talk to that particular process, and then to that particular partition. And that process here will then go and do the work of managing effectively the partition and also the storage of it. So that's what the backend is. So placement here is done by Service Fabric. Service Fabric picks the primary and then also picks the secondary. And the secondary here is effectively the designated secondary owners, it's two, that in case the primary fails, the machine that it runs on gets wiped out, there's already a preloaded, effectively, secondary that will then kick in and automatically take that over. That will happen between, if you're doing 2 cents, that might happen actually between 2 cents. And because we have this separation of gateway and backend, we can actually deal with errors that are happening in the backend, like these failover situations, even in the gateway, which means we can hold the traffic that comes from you, we can deal with issues that are happening below us, kind of in the backend, and then continue the flow when the backend is okay again. And we're doing kind of that buffering for a short time, and that will effectively even out errors that happen, and that obviously increases the reliability that you see, because nothing happened from your perspective. In Event Hubs Premium, we have so in the prior slide, that was Event Hubs Standard and also Event Hubs Dedicated. Like the pool of resources, the pool of VMs is used for all the namespaces, and the placement is happening across those resources without isolation. That also means that if you have a process that through unlucky circumstances gets a little busy, maybe there's one consumer which sends a very odd kind of workload, then your throughput might be, on your namespace might be affected by someone else's workload, because they're sharing effectively CPU without isolation. That goes away with Premium. With Premium, we give you a broker inside of a broker, where effectively you're buying these what we call premium units, and what they give you is effectively cores. So when you buy one PU, you get 2 processors, so 2 virtual CPUs, and 8 gigabytes of memory. You get 2 processes on 2 different hosts, each with 1 core, and a total of 2 cores. If you get 2 PUs, that's now getting a little weird. You get 2 processes, and you also get 1 core per processor, and you get 1 core extra. So when you go from 1 PU to 2 PUs, what we're giving you is an extra, because you're already getting 2 processes and 2 cores here with 1 PU, right? And this is supposed to map to the cores. With 2 PUs, we're giving you an extra core for all utility work, capture, all the things that are happening that have nothing to do with just taking the data and just pushing it on disk. So there's, from 2 PU onwards, there's always a utility core, and that utility core does all the utility work. And the way how we're doing this, we're literally going to pin certain work to certain cores. The way how you're getting these is that we run effectively a namespace broker process that is all yours. And you are literally getting a core hard assigned to that workload. And that's why we need to have so many cores on these machines. So we're building clusters of up to 50 machines, each with so many cores, and that make up our broker. But you get guaranteed cores and guaranteed memory alongside with that. That goes up to 16 PU. With 16 PU, you get 4 processes spread across the cluster, each with 4 cores per process, plus you get another core, another utility core, so 17 cores total in that cluster. So you're getting effectively a cluster in a cluster that's completely isolated for you, but gets the economies of scale that of a multi-tenant cluster. Again, gateway is shared, and that's no problem for it being shared, because there's effectively no noisy neighbor effect on the gateway. But on the broker, there is. So that's what you're getting from Premium. Now, the advantage of that isolation is that we can go and create super even workload performance. Because all the jittery stuff, everything that's kind of affecting your workload, always happens through the sharing of resources. And that sharing of resources is gone here. And the nice thing about this is, of course, because we have the flexibility, you don't need to see, this is not hardwired to a VM. We can go and swap your process to any VMs however we like, and the actually Service Fabric does that for you automatically. And if a machine gets a little hot, that can get swapped over automatically. Compared to Kafka, in Kafka, a partition has a hard affiliation with a node. And then you need to run a tool, the balancer, to go and then move that partition off that machine to another machine. There's manual work involved. There's some tooling that some companies have built to go and do that balancing, but that balancing is not necessary here. That balancing of taking the ownership from one machine to the next machine happens in milliseconds in our system, without anybody touching it. The storage layer that sits underneath it is from the back end talking to the storage system. The storage system in that case, in Event Hubs standard and dedicated, at the moment still, is Azure Storage. Behind every Event Hubs cluster, there are numerous storage accounts, and we can obviously go and add more if we need to. Again, storage is not a thing you worry about in Event Hubs. And we are effectively then taking a partition, and we're assigning that partition to a storage account. Again, with a heuristic about how big that can become. Because storage accounts also have limits, so we need to go and manage how much data you will put there. The way how the writing happens is that we are creating so-called extents, and these extents are append blobs, and we're writing your events effectively into those append blobs while they're open. What we're guaranteeing together with storage is that when we write, that write goes onto disk. So there's no in-memory time when the data is only in memory, as it is, again, in Kafka, where it basically is being committed into the file I/O buffer, and then asynchronously, eventually being synced. But here, we give a hard guarantee that the data is secured on disk once we go and act the receipt back to you, right? That feature doesn't even exist in Kafka. Like, you can't do a sync write. You can do a flush on every message, but that flush will still be asynchronous. But really being the act being in the loop with the synchronous write is something that doesn't exist in the implementation. It is here the default, and you can't turn it off. Once we are reaching a size limit on that extent, we will seal it, and then we will have that here sealed, and then we can go and read from it, obviously. And those extents will then be subject to our expiry policy. And if you are telling us to no longer need your data after a day or 7 days or whatever your policy is that you're setting, that's when we go and then end up deleting those extents. The writing happens from the backend, first of all, normalizing it, the data, and indexing it. So that's indexing the events effectively for faster retrieval. Then we're doing some level of batching if we can. And then we go and run through the optional at-rest encryption model. And then we basically go to the storage provider and then go and write that out to the store. Right? And because we have multiple accounts, multiple storage accounts, that's also how we spread the load, and that's how we also get the IOPS, because we can then go and just spread that across clusters. And all of that writing is happening to zone redundant storage, and that's how you get the triple replication against availability zones at that layer. Yeah. So yes, but we're effectively encrypting at the namespace level. So it's a shared store, right? But the shared store is managed by us. Like everything in the cloud is a shared thing, and all the boundaries of everything that you see are virtual, right? So that's the same here. Everything is at some point a shared resource, and it's our job to kind of set the boundaries. Storage layer for Event Hubs Premium. Picture is a little bit more complicated. What we did here is we have this basic storage model still exists down here, but we put a layer in the middle between it. There is now an extra service fabric application called the local block store or elastic block store. And what that does is so this store here from the back end is also the same, but it has a different block store provider. It doesn't talk to storage, so we swapped that out. So in those machines, and these numbers on those machines are the same. So this is literally just a role that's also added to the back end. We're running these L88IS VMs, for instance, and they have fast 1 terabyte NVMe storage. And we have this engine that we built in C99 that is effectively a block storage that is built on top of these NVMe disks that's inlined into our cluster, and that's doing basically the similar extent management. And then also replicates that data across the cluster in a triple replicated way. And again, here, we guarantee that the data is triple replicated or flushed to disk before we act any individual message. That replication takes consistently under 3 milliseconds across availability zones. To illustrate that a little bit more, an availability zone, right, is a data center. We have 3 of those data centers. The separation between those data centers might quite well be 15 miles. And yet, we're under 3 milliseconds. We are actually in the best cases at about 500 microseconds. So that's that storage layer. That's where that performance comes from. That performance comes from a native code implementation which is consistently fast and is basically self-organizing in Service Fabric and uses the NVMe disks that we have under the covers. That is the layer we have in the middle. The vast majority of writes and reads from Event Hubs come from that layer. And then once we've written an extent, the model is the same. Once we've sealed an extent, that sealed extent then goes into the storage account and then gets there also zone replicated. The chance of losing that data from here is as little as losing data from here, because effectively we're doing something that the storage team does in a similar way, but we're doing that as a highly optimized append log store, which is more specialized than the more general purpose storage account that they have here. And of course, we're speaking a fast RPC protocol here and not RPC, not HTTP, so we're doing effectively as much as we can to speed that up. That internal link, by the way, between the backend and the block store is still using TLS. So we're not taking any chances here on security, but it's our own protocol that we use for that purpose. So that was storage. Networking, we have a firewall feature. So we have, first of all, your namespace gets aliased to a cluster name that has an IP address. That is the IP address you can talk to. That is IPv4 today. We're getting IPv6 ready any day now. So it's going to come within the next quarter or so. There's going to be full IPv6 support also for public. We're using for security here TLS 1.2 by default. But since Event Hubs has been around for a long time, and so has Service Bus, while everybody is super happy to go and turn TLS 1.0 and 1.1 off, there are a lot of workloads which sit somewhere in the basement of someone's data center on a machine. If you've heard Hanselman's keynote about his little box that he has somewhere sitting in the data center, where customers don't know. Our telemetry tells us that there are a ton of customers who are coming to us with older clients, which only speak TLS 1.0 and 1.1, and we will not surprise them with just turning that stuff off. Even though the security gods say, yeah, and it's better if you do, no, because we're not disrupting those workloads. So what do? In a couple of weeks, you will see on the portal a change where you can basically go and set the minimal TLS version for your namespace. That will default, if you have an existing namespace, it will continue to default to 1.0. And then you can up this to 1.2. And what happens is if there is a client, an older client, which negotiates 1.0, and we see that socket, and that socket doesn't match the policy, we will go and disconnect it. Right? Because it's a shared gateway, so the shared gateway needs to go and support that version. And there's no stack that lets us, TLS stack, that lets us get into the negotiation, unfortunately. But if we see the socket not matching the policy, we will go and disconnect it. Okay, so if you are choosing to have a VNet attached, then you can go and make this, you can make a private endpoint, and that private endpoint then gets linked up to our internal IPv6 service endpoint, which means that now all of the communication between your subnet and the service and the event hub in our cluster is private. No traffic goes over the public IP address. And with that, no public routing opportunity here. Right? So that's that link. The great thing is, with that, Event Hubs as well as Service Bus can act as layer 7 routers. Because you can take an event hub and you can attach it to the public network and to multiple VNets. And you can go and use those as effectively layer 7 bridges to communicate across those network boundaries without those networks really being integrated. It is the only thing they can see into all those networks. So a very safe way to kind of bridge between these various sandbox environments through asynchronous messaging. The authorization model gives you two choices: SAS, shared access token, and AAD, RBAC. We have the RBAC, the AAD model. The client talks to AAD with its identity. It asks for a service access token, gets the service access token, and then with that comes to us. And we then check the authorization policy engine given by AD, and then we give you access to write to an event hub or read from it. That's the AAD integrated way. The SaaS model, we have on the Event Hubs gateway associated with the namespace or with every entity, we have a set of rules, and those rules confer rights, manage, send, and listen. And the send and the listen right, if you assign the send right to a rule, then you can go and give someone the rule and the key, and they can go and make a token, and once they make that token, they have send rights in that token, and they can use it. It's not an identity, it's not an account. It's a rule that's conferring rights that has a signing key associated with it. That means that you can use it directly for a client, but you can also use it for a custom token service that you can go and write yourself, a simple Azure function, for instance, where you walk in with whatever identity you have, right? And then you say, I would like to have send access to this event hub in some way. And then if the service believes you, it can go and create a token for you, which can be valid for a minute, which can be valid for 3 hours, however you want it. And that's what you get back to the client, and then the client can go and talk to that event hub. So it is a highly customizable model that is not carrying all the weight of AAD if you need to have your own thing. But you can also use it like a username and password. Okay, so replication federation. If you want to go and replicate data from one event hub to the next event hub, then you had to write code before 3 months ago. We changed that because there is often a need to go and replicate data across regions or to distribute data between event hubs from different owners, many different scenarios. So what we did is we teamed up with the Logic Apps team, which built an automation task. So if you go on the portal on an event hub, you will find a tasks preview panel. And then you can go and add a task to an event hub. For instance, you can replicate from an event hub to an event hub. You can also replicate from an event hub to a service bus queue. You can replicate from a service bus queue to or a subscription to an event hub. So all the combinations between our services. Then you go and connect them. You start with the event hub that you're doing this on, and then you can connect another event hub, and then you add effectively a new task that is naming the source instance, naming the consumer group, naming the target, and then you create a logic app in the standard plan. You can create a new one, or it can assign to an existing one. Press create, and then automatically that task exists and runs for you. And the great thing is it has complete visualization also in the Logic apps via application insights. So you can actually see where the data comes from, where the data goes to, what the latency is. All of that is already built into the portal. It's a with monitoring, automated, no code, just click integration between all those services where you can now go and create routes between things across data centers with your messaging resources. Okay, lastly, performance. Event Hubs Premium, and specifically about Event Hubs Premium because that's the future storage technology that we have. The latency, end-to-end latency for 4 PUs with 1 megabytes per second throughput, and here's the partition count that goes with that, right, is under 10 milliseconds. 10 milliseconds. Ingest, triple replicated on disk, all that circus that I just talked about, getting a message out, retrieving on the other side. 10 milliseconds. Kafka and Event Hubs Native. Event Hubs Native tends to be a little faster because AMQP is a more optimized protocol than the Kafka RPC protocol, but we're talking about under 10 milliseconds. For that 1 megabyte per second workload, consistent. If you are in that workload, in your workload tier, it will be a flat line in terms of latency. Here's what that looks compared to some other Kafka cloud provider that you can go and buy something from, and that's what their latency looks like. Ours looks like this. right? So that's, again, 1 megabyte per second throughput. If you go 10 megabytes per second, 20 megabytes per second, then we go up to 20 milliseconds maybe in terms of latency, right? But the other guys go up to 80 milliseconds in latency. We are twice as fast when the other guys have a good day. So this is enormous performance, and that enormous performance will eventually also come to the other SKUs. And the key thing for premium is it's predictable. It always is like this. And that's what you get out of resource isolation. That is because we have effectively a virtualization model here in Event Hubs that is sub-VM and flexible across the system. And that gives you that flexibility. Global reliability, the uptime is something we don't even track. Our clusters don't go down. Yes, there may be times when someone does a BGP thing, and there may be times when DNS is down, right? That's all things that are beyond our control. But is Event Hubs available to go accept connections? Yes. When clusters go down, that's an anecdote from years ago. That's how we think about those things, right? That doesn't mean that there aren't errors and that things aren't happening, but uptime, availability to go and get a connection is always there. Because the clusters are giant, and because the clusters are spread across availability zones, right? That's the point. The weekly average reliability, which means you try an operation, and does that operation succeed, exceeds 6 nines. Exceeds 6 nines, right? I just looked it up this morning. Current weekly availability for this last week is 99.99992. And that is across the entire global footprint with all the upgrades and all the changes and all the machines that get updated and all of that. Everything is counted in. That's where we are in terms of reliability. It's ultra reliable. So, that all said, I'm 2 minutes over, unfortunately. So we have a great broker. It's industry-leading reliability and availability. I hope this was insightful in terms of getting you some insights into how we do things. It's very different from a thing that you can run yourself. And the way how you get one of those things is you fill out 3 fields in the portal and you press the button, and then it takes a few seconds and you have one of those. That's the effort. You can't do that with a Kafka broker. Have a good day.